This is the second part of activity 4, and I hope that you went through and you highlighted, forgive the error on this one, that you highlighted the equivalent strings, circular permutations from who went first, and yet the order was the same, because we're going to use them to answer this question 6 and question 7. You know, based on those answers for questions 3 through 5, how many equivalent outcomes are there for each seating arrangement? Well, each seating arrangement consists of 4 elements, and there are 4 officers in the original problem. So there are 4 equivalent elements for each seating arrangement. In fact, what I could continue to do with coloring this string out is I could say P, VP, TS, President, Vice President, Treasurer, Secretary, is the exact same here. And so every single one of these could be identified to have a matching arrangement. Secretary, President, Vice President, Treasurer, and then Treasurer, Secretary, President, Vice President. So I did box. This should not be highlighted green, but it should match the squares. There are six table arrangements, just depending on whichever one that gets you to start first. And then from there, you list out your remaining officer elements from that starting point. But in each of these columns, there's actually an equivalent arrangement if you think circularly. The seating arrangement problem is an example of circular permutations. The number of circular permutations of n objects is n factorial divided by n, which is what's happening here. There are 6 arrangements, 4 people. There's 4 people. Get this right. Yep. So 4 officer positions. And then it's circular, so we divide by 4, which when you do the divide by 4 process, you're essentially just saying, I don't need those columns, or I don't need those columns. But within this one column is every arrangement of the officers, the 4 elements from that column. So this becomes 4 factorial, 24, divided by 4, which is 6. Oh, mathematically. We have a formula, 4 factorial over 4, and it tells us how many numbers are in this list because they're just repeated these other times. Circular, we just repeat, we just put a different number first, but then the order continues from there. So we have a formula for circular permutation, and over here on this side, a circular permutation is a permutation where there's no starting point and no ending point, because the order is the only thing that matters. Not which goes first, just what's the arrangement. If we use our formula, calculate the number of table arrangements for each number of officers. I'm going to do the first one. You should do the rest, and then just pause and skip to the end of the video to see if we line up. Calculate the number of table arrangements for each number of officers. If there are 5 officers, then the formula says 5 factorial divided by 5, which is the same as 5 minus 1 factorial. 24. Why don't you do part B and part C? Skip to the end, see if we got lined up answers. Formula, use it. Question to consider as you're getting ready to move forward. Demonstrate how n factorial over n is equivalent to n minus 1 factorial. Like this. N factorial over n is n times n minus 1 times n minus 2 times n minus 3, multiply all the way down to 3, 2, 1. And we're dividing by n. So this n and this n, they're not in parentheses. They are factors. They reduce to 1. And what you're left with is n minus 1, n minus 2, n minus 3, n minus 4, all the way down to 3, 2, 1, which can be rewritten as n minus 1 factorial. So here I go, part B. 120. There are 24 arrangements. There are 120 For 6 officers, using the formula for circular permutation, there are 10 factorial over 10, which is 10 times 9 factorial over 10. 9 factorial is math time, so 9 menu 5 1 362,880 seating arrangements for 10 officers. Good with that. Thank you guys for liking, commenting, and subscribing. We've talked about permutations, factorials, and now circular permutations. The following activity, activity 5, is going to be on combinations. And we want to make sure we understand how a combination is different from a permutation, but we've already been teasing at that idea. So stick around, click on the next video. Thank you for watching. I'll see you in the next episode.